It's time for another episode of Rust in Production, a podcast about companies who use Rust to shape the future of infrastructure. I'm Matthias Endler from Corrode, and today's guest is Charlie Marsh from Astral. We talk about improving the Python ecosystem with Rust. Charlie, thanks for being a guest. Can you say a few words about yourself and about Astral, the company you work for?
Yeah, of course. Thanks so much for having me. First of all, my name is Charlie Marsh. I run a company called Astral. We build high-performance developer tools for the Python ecosystem. So we're best known for two tools, Ruff, which is a sort of combined linter formatter code transformation tool. You could think of it like kind of Rust format and Clippy together, which is, again, for Python code, but written in Rust. And then UV, which is our project manager, Python package manager, Python toolchain manager. It's you could think of it a little bit like Cargo and Rust Up. So it tries to will bootstrap Python for you and then help you manage your dependencies, install things, lock them into lock files and reproducible versions and all that kind of stuff. So yeah, everything we've built so far is open source and written in Rust. We're a team of about 15 people spread from the Pacific time in the US. We have people in Pacific time, Central time, Eastern time, and we have one person in the UK. We have 4 people in CET or like Germany, Switzerland, the Netherlands, and then one person in India. So not only are we like remote, we're like very distributed, kind of like a lot of open source. And we spend all our time basically writing Rust to try and make Python better.
I heard about Astral the first time when you published Ruff, but it took off with UV, I would say. Like there was definitely a huge sympathy for what you do in the packaging space as well. Did you see that as well from a company perspective, that there was a huge growth?
I think so, yeah. I mean, I think, we started with Ruff. I started working on Ruff before the company existed, and it was just something I was building. Well, for a lot of reasons, but largely because I saw these were problems that I had experienced in my own projects. And I was like, what would it be like if I wrote, Python tooling in Rust instead? And that was sort of the genesis of Ruff. And Ruff grew extremely quickly. Like we had, decades old projects like SciPy and stuff, like adopting it while it was still like what I would consider to be very unstable. So it was clear that people wanted something in this arena of faster Python tooling. So Ruff grew very fast, and we were seeing what was happening with Ruff, and we were like, well, as a company, and in terms of like the problems we're trying to solve, like we're not trying to build just that. Like we want to build a Python toolchain effectively. Like we want to solve the hard problems in Python. And for me, like packaging was kind of like, if you want to be like the Python tooling company, which aspirationally, I guess we'd like to be, then like you have to work on packaging, I think, because it's the thing that everyone has trouble with, and the thing that has been so many people have tried to solve and done good work on, but I don't think anyone would consider it solved. And so, I kind of knew from early on that we wanted to do something in packaging. And before we released it, I definitely felt nervous in that Ruff had grown well and people really liked it, and it was kind of felt like it was going to be a tough act to follow. Like we don't want to be a one-hit wonder, with the tools that we built. Like I wanted to build something that hopefully would be as exciting and grow as well, and have as much of an impact as Ruff. And I think UV has actually really surpassed that in a lot of ways. It's like I think the impact it's had on Python has probably been more significant. And I think like the not that I don't love Ruff. I mean, it was my first my first big project, and we still, like, half the people on the team are working on Ruff in the static analysis tooling. It's like a big focus area for us. But I think I've been really amazed by how quickly UV has had the impact that it's had. Like we released it in February of last year, so it just turned 1 year old, and in that time it's grown to like, I think last I checked, it's like a little over 12.5% of all requests to the Python index come from UV, which is like over 200 million requests a day, which is wild, right? And, I spend a lot of my time talking to companies. There are tons of like $1 billion, $10 billion, even $100 billion companies that are using this thing in production and have been for a long time. So just like the way it grew, I think really surpassed my expectations. And I feel like we now have a platform to like keep hopefully making Python better. But I think you're right that like UV, I think we shifted into a little bit of another gear. We spread beyond just being like the company was just Ruff before, and now we are like Python tooling, and we try to solve like a much wider surface area of problems.
Now, you said that Ruff was your first major Rust project, maybe the first actual project that you tried after like learning Rust. I'm not sure about this, but it certainly was a big milestone for you in your Rust journey. But then you compared it with UV, and did you already learn a few things that you wanted to avoid with UV that you did with Ruff? And also, did you set up the UV code base early on for such growth?
Yeah, so I would say I really learned Rust in the process of writing Ruff. I had done some Rust at my previous job, but someone else on the team like introduced Rust, really great engineer. And when I was contributing to that code base, I was mostly trying to get like in and out as quickly as possible because I didn't really know Rust. I was like, I need to fix a bug. How do I get this to compile? Right. I wasn't really taking the time to learn it. I was just like using it when I had to. So I had some Rust exposure. But part of why I worked on Ruff in the first place was I felt like I wanted to really learn Rust. And I thought that in order to do that, I had to build something from scratch. And I had to like, it's just kind of the way that I like to learn. I was like, I need to build something. And like, even if that requires like wasting a ton of time trying to understand like lifetimes, like maybe I'll burn like 2 days trying to get this to compile. But like, that's kind of how I learn, is just like, I have to build things and like fight through the problems. And I wanted to learn the ecosystem and just the tooling and everything. So I did really learn Rust in the process of writing Ruff. I think that showed, like there was probably still shows a little bit today, like, you know, especially early on, there were a lot of things I was doing that were just that I would now, well, I mean, this is part of personal growth, right? There's lots of things I was doing that I would now look at and laugh about and say, that's obviously not the right way to do it. Whether it was like silly performance things or the way I was structuring the code or I don't know, anything. By the time that we started working on UV, I think I felt a lot more comfortable in Rust. And I'd also learned more from looking at other projects too, I think. And we had kind of evolved Ruff a little bit over time. So for example, like we have a fairly wide like crate structure. Like we just create a lot of crates. Like if you go and open up Ruff or UV, the crate subdirectory, there's like in UV, there's at least 20 crates, maybe like 30. So we just create like lots of crates. And that was something that I started to do in Ruff because our build and compile times got really bad. And it became like, if I just put everything in one crate, it was like our build and compile times got worse and worse, and the development loop was painful. And you know, at the time I was reading a lot about how sort of like crates are like the atomic unit for like Rust C, and like you can parallelize across crates, and you need to be thinking about like how your crate graph looks so that there's a lot of like fan out and stuff. And I was like, okay, we're going to start creating like lots more smaller crates, and we're going to sort of change the atomic unit of like what the code base is from like the module to the crate. And so we started carving out like lots of little crates, and we did basically the same thing. And for example, in Ruff, like, you know, like the core linter crate like doesn't depend on clap, for example. Like it doesn't depend on any of the CLI stuff. The CLI stuff is in a separate crate that depends on the linter crate, and you just try and get this structure in this organization. Or like the parser and the AST, those are all their own crates. So we can, if you just need to test the parser, right, it's really fast to compile and build. Or if other people even just need to pull in the parser as a library, which some people do, it's much easier. So by the time we got to UV, I think we had ironed out a lot of things that made it so we just put a lot of stuff in place from the start. Like we just had a better separation in terms of what went into what crates. I think we'd ironed out a lot of our workflows. For example, like what's our Clippy configuration? How do we pin the Rust toolchain version? Like how do we install Rust in CI? Like there were just all these little things that we were able to just copy over from Ruff. And I think that made things a lot easier. At the same time, there were still a lot of design decisions in UV architecturally that were pretty different, because the design of a package manager and the design of like the linter are just, the things they need to do are very different. So, for example, like UV has a whole networking stack, right? It needs to like make lots of HTTP requests, and like the linter doesn't need to do any of that. So suddenly we had to think about like, like requests or like basically the whole HTTP stack. We had to think about like OpenSSL. We had to think about all these system dependencies like Git. That was another too. Like we support Git dependencies. So suddenly you have to think about how you depend on Git. I think there was just a lot of complexity that came with building a package manager that we didn't necessarily have to encounter when we were working on the linter, which is good because I kind of like encountered those problems over time.
When I understand you correctly, to summarize, you didn't have a rough start with UV because you could copy over a lot of the, let's say, templates or a lot of the best practices from the previous project.
At least what we thought were best practices. Yeah. And I guess to some degree, what we still think are best practices.
But when you used UV, when you started with UV, did you already compartmentalize some of the functionality into smaller crates somewhat subconsciously? Did you say, oh yeah, this definitely goes into a separate crate now? Or did you still start with a single large crate?
No, I think we were like compartmentalizing stuff basically from the start. And for example, like, we had one crate for like parsing Python versions. There's a whole spec around versioning that requires there's a lot of intricacies to it. And so that's its own crate. We had one crate for like parsing requirements TXT files. That's another thing that's common in Python. There's actually no spec for that. That's like implementation defined. And so we have like one crate for that. We have a crate for creating virtual environments. We had a crate for the CLI. We had a crate for the resolver. So we broke things down, I think, pretty early on. And that's generally served us very well. So I'm a big fan of that structure. I think it's like the trade-off is really different when you're publishing a library. Like we don't publish anything in Ruff or UV as a library. Like we don't publish to crates.io any of the stuff that we build right now. Like the public API for our stuff tends to be the command line. So the CLI, the command line interface. So like if we had to publish things, I think we would have to think a lot more carefully. Well, there's all sorts of considerations that come with publishing that you don't have to think about if you aren't publishing. But like one is if we had like a really granular crate structure, I think it becomes a bit harder for people to use there's a lot more of a maintenance burden, and it's also harder for people to use and compose your things.
But you don't go and introduce a crate for types specifically, because that's one thing that I see some people do, some companies do that. They have a types crate where they put everything that is related to, their basic types into one thing. And then at the end, they don't really get a lot of benefits from using a workspace because you need that types crate anyway in all of your other crates. And so it kind of goes against to what a workspace is about, in my opinion. But I want to hear it from you. Like, what are some anti-patterns for building workspaces?
Yeah. So like, I guess, we try not to do things like that. I don't know what we would call that pattern, but like create a crate that's just kind of like used everywhere. There's maybe some of that, but we try to generally avoid it. I think the other anti-patterns are like, you can make your crate structure like too granular. Like if you find yourself creating a crate that's like one function, and sometimes you'll find yourself doing that because you have like circular dependencies or something in the dependency chain that's requiring you to do this. Like I have two crates that need this functionality and they can't depend on the other or something. And then you find yourself putting a function into like it's just a crate that's like a function. At that point, you've probably gone too granular and you kind of need to rethink like the organization, because there is some overhead to having all these crates, and like, it's not always like super fun to maintain. I think a couple of things that we do though that are kind of nice for this is like we prefix all the crates in the workspace with UV or with Ruff. So like it's easy to differentiate what's a crate in the workspace versus what's a third-party crate. Like all of our crates are like UV virtual env or like UV resolver or like whatever else. That's pretty nice. And then the other thing is we declare them all in the workspace root. so that every crate that depends on other crates in the workspace can just use workspace equals true. This is a little bit nuanced and maybe hard to visualize, but it basically means that like in the cargo.toml for all the crates that are in the workspace, it's very obvious what else is in the workspace. Another thing that we do is we actually try to use workspace equals true for basically all dependencies in the workspace. So we put everything that we depend on in the root cargo toml, like the workspace root, and then we use workspace equals true everywhere. And that tends to simplify things a lot. It basically means we have like one dependency specifier for request, for example, and a common set of like default extras or no default extras, or sorry, not extras, features. Extras is the Python version, is the Python analog to features, but like no default features or, or whatever else. We have like one dependency declaration for everything that we need. And then all the workspace members, their cargo tomls are just very straightforward. It's like the things they require with workspace equals true. So we don't have to think about, oh, do we have request dependency specifiers across like 10 or 15 different crates? We just have one definition for it. So like that's also, I think, been a really handy thing.
Right. Workspaces seem to be one of these things that I keep missing in other ecosystems. And I can't remember if there's even another language that has such a feature. From the top of my head, I can't think about one.
I mean, we've thought about it a fair amount in Python. So like UV has workspace functionality that's like very much modeled after cargo.
Mm-hmm.
So you have a root, it defines the members. We use very similar, actually, like members and excludes syntax. And there's nice things like that. You can do like UV run -p, just like you can do cargo run,
nice.
Right? So like we've just like copied a lot of things from cargo because it's great. And we're like, we want to have those things in Python. And for workspaces, I think that's worked really well. It's been very interesting to introduce them because for a lot of people, it's a fairly new concept. Like when they come to Python, right? Like most people who use UV have never used Rust, right? They've never heard of a cargo workspace before. And like, why should they, if they're just working in Python? So it's been interesting to try and like communicate that and like help people understand like what it's for and like why you might use it and like what an example workspace might look like in practice. There are some things that we miss that are a little bit hard to get like without standards. Like for example, we don't support, I just spent all this time talking about this incredibly boring workspace equals true thing that all your listeners are probably like, why is he spending so much time talking about that? But like, we can't really do that in UV because like, there isn't really a way to express that in the standards. And so, there are some things that we have to kind of either can't support or have to get creative about how we support. But I think the workspace concept is excellent. And like, I'm really glad that we made it such a first-class thing in UV.
Now, I'm pretty sure that we could talk about workspaces for hours because there's a lot of nuance to it. And I think a lot of people that haven't tried it themselves, they just don't know what the fuss is all about. But I do believe that there's more to it than just the term. Now, one other thing that you mentioned, though, which is very close to my heart, is parsing stuff, especially the requirements txt, which is unspecified, I heard. Now, isn't it super
defined? Yeah.
Isn't it super simple? Like someone might hear this and say, oh yeah, I just open my editor, I string split every line on the equal sign, and that's my requirements txt parser. Why is that not the case?
Yeah, so for requirements txt, it's like, this is a file format that exists for pip, really. Pip is like the, I guess, sort of, how should I describe it? Like the reference implementation for a lot of things. It's really been like the Python package installer for a long time. Yeah. And requirements txt is a file format that exists for pip. And, kind of the way that you can think about it, which maybe people don't think about it this way, is like, it's basically like each line is a command line argument. Because you can not only put requirements in there, you can also put command line arguments and settings. Yeah, which is interesting. So like in pip, you can pass an index URL on the command line, which is like, what registry should I use for fetching packages? You can actually put that in requirements txt too. You can just do -- index URL. You can also like embed, like you can also nest them. So like within a requirements txt, you can do -r and point to a different requirements txt. And then it's sort of like it gets inlined roughly. So there's a lot of complexity to the stuff that's in requirements txt and that people don't really think about. And there are also lots of very subtle behaviors where especially for us, we often have to decide, well, what do we want to do? Do we want to be like bug for bug compatible with pip, or do we want to do things like slightly different? And a lot of these are edge cases, but there's just a lot of nuance to it. Like in a requirements txt file, you can have, I guess, what I would call like a named dependency. Like you could say like Flask and then the version that you want, or you could do Flask at and then the URL that you should fetch it from, or like a Git repository or something like that. But you can also just do the URL or just do the Git repository. And it turns out that in pip, there's like slightly different behaviors around how those things are parsed, like the URL, if it's just the URL versus if it's after a named dependency. And how white space is handled, like error recovery, like all this stuff is just like a little bit different. And so over time, we've had to add, like basically the only way to know if we're doing the right thing is we just see what pip does, and then we like try to mimic that to some degree. Or if we think we can do things that are unambiguously clearer, then we'll do that. But it's like that one's especially hard. It's a little bit easier for other things like Python version specifiers, where there's like a clear standard on like how these things should be parsed. And if we see something that's not clear, we can actually like ask about it through like the standards process and be like, how should this be handled? Like blah, 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 blah.
In essence, you make the standard stronger for everyone, which is great. What kind of piqued my interest there was, did you have to go and read the pip source code to be able to understand what's going on? Because this is a standard that sort of developed over 30 years. I think Python is 30 years old by now. It's from 1994, as far as I remember. So, and did you really have to read the source code?
Yes, sometimes we definitely have to go read source code, and which is fine. Like I don't really mind that. Like as long as we can figure out like why a certain behavior exists in a certain way and like what it's motivated by. But yes, we often have to go read the source code to understand like how does this tool handle this case, and like and also why, right? Like a lot of the time you're trying to understand why people made certain decisions, not just how it works.
That means you don't only have to read the source code, you also have to read the history, the version history, the commit history. But do they have proper tests at least where you can go through and maybe implement these tests in your implementation?
Yeah, they do have tests. Yeah, it's not always like super straightforward to take their tests and move them over to UV. Like a lot of the times, I don't know, just the way that you write tests in like Python and Rust often tends to be quite different. Like, or at least the way that we write tests tends to be quite different. Like, like in Python, like mocking is very popular, for example. And like, we have like almost no mocking in UV. Like almost all of our tests, I think, are what you would probably consider like integration tests. Like the whole way that we test UV is we actually run real scenarios against a real package registry. And it's almost all based on snapshot testing. So like we snapshot the CLI output. A lot of the time, that's like how we detect if things are working correctly or not, is we snapshot the CLI output, or we snapshot the log file, or we snapshot things like that. But like the vast majority of the way that UV is tested is integration tests of running real commands on the CLI and snapshotting the output. And that's like, we have a lot of tests and they all run through that. So it's like a little different sometimes, because if I go and look, we do have like obviously more traditional like unit tests, like for requirements.txt parser, like that's something that's very testable, right? And we do have tests for that. But often if it's like more complex scenarios around how pip behaves versus like how we behave, it's a little bit harder to like shoe it into what we have.
Do you always run the full test harness?
In CI?
Yeah. Or maybe locally as well, but I wonder, that's probably too much.
Yeah, we almost always run the full test harness. So like we skip it for changes that are purely documentation, which we just detect with some file filters in GitHub Actions. But otherwise we run the full test suite. Every change we run it on Linux, Mac OS, and Windows. And that's because we do like that's not as critical for Ruff, but it's very critical for UV, because with the package manager, just like more things tend to differ across platform. more behaviors differ across platform. And so we always test everything on Linux, Mac OS, and Windows. I guess one interesting piece is like we build UV for like a lot of different targets. So, when we publish to PyPI or publish anywhere or publish to GitHub releases, like we're building like 15, probably somewhere between like 15 and 20 different builds, or maybe is it 15? Somewhere between 10 and 20, let's just say, different build variants. And so that's like Linux x86, dynamically linked against glibc, Linux x86 muzzle, Linux Arch, glibc, Linux Arch muzzle. We build for some more obscure platforms that are supported in Python, like PowerPC and like S390X and stuff like that. We build for ARM and x86 Windows, ARM and x86 Mac OS. So we just have like a lot of different builds. And I mean, setting those up to actually build is fairly complex. And so if you ever find yourself needing to do that, you should look at RCI because we've just figured out how to build a Rust project across all those different, like a lot of those are cross compiled, right? And we've just figured out how to like build those across lots of different machines.
What is RCI?
Our CI.
Your CI. Oh,
yeah. Just go look at our .github folder and like take stuff from it.
Mm-hmm.
But the other piece is we actually we rerun all of those builds whenever certain files change. So like if we add a new dependency, we rebuild across all those machines, which is fairly, because we've run into situations where we add a new dependency and then we go to release and then, I don't know, the ARM muzzle build fails for some reason that we don't, or the Windows ARM build fails for some reason that we don't fully understand. And so now we run those. I guess the only nuance is we do rebuild everything on every platform if we, for example, change our dependencies.
Yeah. I think this is kind of where the Rust build system also has its limits at this point in time, because especially when you talk about like feature flags and maybe optional dependencies, dev dependencies, there's a lot of loose ends. And sometimes you can't really specifically and exactly say which dependencies you want to enable for which platform. And, on top of it, you have various system dependencies and the build.rs files to go with it. And sometimes you don't want to have a system dependency on a certain target and so on. And it's very hard to work around these limitations.
Yeah. I mean, a lot of the complexity has come from things like allocators. Like, like we use, I don't even know how to pronounce these things, JMalloc, right? Like on most platforms, but like it just like doesn't work on like, it like doesn't compile on like some platforms. So we have to have like a bunch of build configuration around that. The other one that caused a lot of trouble was our like zlib implementation. Like we wanted to use, which is like for decompression, like we wanted to use, so like by default, you get this PureRust Minez oxide implementation if you just use like Flate and like request, like if you just use like the request crate to like decompress stuff, you get like this PureRust implementation by default, I think. But there's like this zlib ng version that you can use, which is a lot faster, but it requires like, it adds like a CMake dependency and it needs to be built. It's like very hard to build. And so we could never get that to build on certain platforms. And so we had to have configuration around that, around like, where do we enable it and where do we not? We actually totally tore that out recently and moved over to zlib.rs, like the PureRust implementation of a lot of these zlib optimizations, which in our benchmarking at least is actually both faster and it's like way easier to build. So when you get something that's PureRust, like it's just like it simplified things dramatically. We just like tore out this like CMake dependency and like all this stuff and got rid of all this configuration, because now we can just use like the faster, easier to build, more portable like Rust version on all platforms. So a lot of it comes from, if you're trying to do things that are more like customized or like bleeding edge like that, like you use really fast system dependencies or like allocators, like you end up running into these kind of configuration problems. But we've tried to make that simpler over time.
Must have been such a relief to pull out that CMake file.
Oh, it's amazing. It's amazing. I actually tried to do it anyway, sort of long story. I tried to do it like a few months ago, and then we realized that they were using compile time feature detection for a lot of the optimizations. which isn't great for us because it meant that like on x86 things were actually a lot slower because we have to build for like a common CPU target. Like, and they recently re-released with like runtime detection, and I was like, okay, cool, we're doing it again. So I redid the change like twice, and like redid all the benchmarking on like my Windows machine and on Mac OS for ARM and all that kind of stuff. So yeah, but like, when you can get rid of stuff like that, it's like immensely helpful.
I realize whenever I read one of your posts or whenever I see you talk, I realize that you care a lot about performance and you benchmark a lot and meticulously. And do you have any tips for people that want to make their Rust code even faster from like doing it so often? There must have been patterns that evolved over time. What is a good benchmark? What's a bad benchmark? What are some good libraries out there? In general, what are best practices? What don't you measure, for example? That sort of thing.
Yeah, there's like so much to share. I mean, it's like actually like learning the tooling too around benchmarking is like itself a skill. And like we have people, like there are certain things that I only know how to do on Mac OS and I don't really know how to do on like Linux or Windows. And like there's other people on my team who would know how to do these kinds of, like I know how to use instruments, for example, on Mac OS. And that's like its own set of things. I think for us, there's like a bunch of different forms of benchmarking. One is like micro benchmarking, which is, I guess, like generally like the kind of thing that you would do with Criterion or a similar crate where you're like running typically fairly well isolated code on test inputs and running like thousands and thousands and thousands of or millions of iterations of it and trying to detect very small changes. That is incredibly useful thing if you can isolate your code in that way. So like if I'm trying to figure out, for example, if like there's two different ways that I could write this function that like parses this very simple string in this simple way, and I'm like, I want to know which one's the faster way, then like I'll do something like that. I'll try and just isolate like two methods and then use like Criterion or something similar. We also do micro benchmarking on CI. So we use a tool called CodSpeed, which does like continuous benchmarking, continuous profiling. That again is really good when you have things and they run it on Valgrind. So like basically, like if you just try and do this kind of benchmarking on like a GitHub Actions machine, it tends to be extremely unreliable. You have to have like a very high error tolerance. Like when we very early on in Ruff, when we started adding continuous benchmarking, we did it on GitHub Actions, and we would just regularly see like 5 to 10% fluctuations, even for no op changes, because those machines are very noisy. So CodSpeed kind of solves this problem because they run all your stuff under Valgrind, so they get like a much cleaner snapshot of like what's actually changing in terms of performance. There's some nuance to it, but like basically, if you have code, I/O can make things like really messy with benchmarking in general. But if you can write benchmarks that don't have any I/O, that are very pure CPU, you can fit them into that kind of micro benchmarking framework. It's like incredibly useful, especially in Ruff, where we have a lot of that. We just run that in CI. It catches things all the time. Real positive changes show up in, get flagged as positive changes. Like it's a fairly high signal. So that's like, if you can do that, that's great. We can't always do that in UV. We often do more like, I just sort of make these words up, like macro benchmarking. I don't know if that's a word, but that's like, I use Hyperfine usually, and I will compile 2 UV release builds, and I will run some operation over and over, and I will try to see if I can detect a difference. And I'll typically try and minimize I/O as much as I can, but maybe it has to read from disk for the on-disk cache. And like there, it's like you're trying to find much smaller or it either needs to be really obvious or very consistent in order for you to catch anything. This is like one form of benchmarking is, it made everything 10% faster. Then it's like very obvious that it made things faster and you can catch it in that kind of benchmark. The other pieces that you can look at, which are a little bit harder to do direct comparisons, but we will do a fair amount of like, there's a great tool called Samply, which we use it's a sampling-based profiler. So like you can just run a UV command. You just prefix it with Samply, and then it opens up a flame graph in your browser that has, all the flame graphs of everything that got called and where you spent time. And so that's often a way that it's a little bit harder. you can't always tell just from a flame graph if you made your whole program faster, right? You can tell if you ran the flame graph, you found something that was taking up a lot of time, and then you make changes and then it's gone. Like that's good. That means like you got rid of that time, but like that alone is not enough to tell that your program got faster, right? That's just that you removed that thing that you were spending time on, but maybe it went somewhere else, like blah, blah, blah. So we'll often do that as a way to diagnose issues. And if something's slow, then we'll be like, let's run it under sampling and like see where we're spending time, for example. And so there's like certain tools you want to use to diagnose issues, and then certain tools that we often use to try and like confirm findings or understand if there are regressions or anything like that.
Yeah. In my mind, when you said sampling, profiling, and flame graphs, I was sort of hoping that the tool would kind of update the chart as the program runs. I'm not sure if that's the behavior of that program.
I don't think Samply does that. I think there might be a way to like compare to flame graphs, and like Codspeed tries to do this. They'll try to diff the profiles.
Mm-hmm.
It works okay. Sometimes it's hard for them to, I mean, it's like inherently that seems like a very hard problem. Like they have to try and align like what two function calls are like the same. Like it's not necessarily always trivial because code is changing, but like there's some stuff like that.
But
yeah.
Just for context, maybe someone might not know a sampling profiler. How would you describe that in a sentence or two?
I mean, my understanding is it basically watches your program execute and it samples at some rate. So it takes a bunch of samples as your program is running to try and get a representation of where you're spending time. So maybe it takes, just for stupid numbers, maybe it takes 1,000 samples and or let's say 100 samples, and in 10 of those, you're in this function, then, it would say, hey, I found this, we were running this function 10% of the time that I sampled, and here's where it was being called from, and like, here's how you're spending time. So it basically watches your program execute and tries to figure out, based on probabilistically by sampling the behavior, where you're spending your time. That's my understanding. I never built one of these, so it actually might work totally differently than that. But that's my understanding.
No, that's also my understanding.
Which is a little different than like in Valgrind, for example. Like Rust. I know Rust C, I think, does this too. Like you can do profiling based on instruction counting. So like you actually look like the instructions that are generated or executed or whatever, and you try and do something you don't look at the behavior of the program. You don't like run the program. You try to look at you run the program, but you look at a different thing. You're not focused on time, like wall time. You're looking at like what instructions are being executed, how many instructions are being executed. So it gives you a little bit more of like a quantitative look, I guess, at like where you might be spending time. And I believe Rust C has continuous benchmarks that look at. I could be totally wrong. There's something that I've been shown before in the Rust ecosystem that does continuous benchmarking based on instruction counting.
I was kind of thinking that Cargo Flame Graph would do that in comparison to Samply. I never used Samply before, but my go-to tool for flame graphs is always Cargo Flame Graph. I'm not sure if you've used that one.
I think I have, but it's been a while. Yeah.
And you find Samply to be more ergonomic?
I found it to be easier. Yeah.
Mm-hmm.
Yeah. Okay. It's just like what we tend to use on the team. But like, I'm sure that there are lots of good options, but it's just like, it just works seamlessly across macOS and Linux, which is really nice. So like a lot of these tools will be like, it's maybe hard to get them to work on one or the other, for example. Not always. I don't know if that's true of Cargo Flame Graph. I just mean like of things we've used in the past. Sometimes it's like, oh, this works great on Linux, but not really on macOS. And I think Samply tends to work really well on both.
Cargo Flame Graph gives you an SVG file that you can open in your browser, and it's sort of interactive.
Yeah.
Pretty basic as well. I don't know if there's probably support for the Chrome profiler, which also supports flame graphs, but I'm not sure.
Yeah. The thing that Samply gives you in the browser, you can like click into the flame graph. You can filter by name. You can filter traces by name and stuff. It's pretty nice. But again, like some things are just really hard to understand in a flame graph. Like, if you have a lot of like UV is very async, and like we have like different stuff going on. And so sometimes it's hard to tell like where time is actually being spent. Like it's really, things that are spending lots of CPU time are always nice because they're obvious and you can find them and fix them. But things where it's like, oh, the scheduling is like slightly off, or like we're waiting here, but like blah, blah, blah. Like those tend to be harder, like more pernicious bugs to find.
By that definition, isn't it true that profiling or benchmarking Ruff is easier than UV because Ruff is inherently CPU bound. You do a lot of computations, I'm assuming.
Yeah, I think it's much easier. Yeah, like Ruff does have a fair amount of. It does have I/O, right, in the sense that we're reading files from disk to analyze them, but that I/O is, I would say, like, it's a lot more stable and more minimal than in UV. And also it's kind of like, sort of like happens up front, like we read the files and then we analyze them. Whereas in UV, there's kind of just like constantly I/O happening, whether it's we're reading stuff from disk from the user's project, or we're reading stuff from our on-disk cache, or we're making small HTTP requests or large HTTP requests. We're downloading and unzipping files. Like there's just constantly I/O happening. So it tends to be a bit harder to benchmark. Often we'll benchmark by, we'll actually run UV with the cache, because at least then it's a lot more stable. It's like we're doing the work, but we're like reading from the cache every time, as opposed to if you want to benchmark anything that requires like network I/O, really hard. It's very hard because the amount of variance that you'll get is, you will usually dwarf like anything that you would see in CPU code changes.
That is true, but at the same time, you have to be careful not to change your targets. You need to be sure that you're benchmarking the right thing.
Yes, absolutely. Yes. And we do make a distinction between that. We think of it as like warm performance versus cold performance. It's like performance when you have stuff in the cache versus when you don't. And we do look at both. There's some things you can do, like you can set up a network link conditioner. That's what it's called on macOS at least. So you can intentionally throttle your own network connection to try and get it to be a bit more consistent, like bring it down to something that would hopefully be a bit more consistent. But again, that's also different because, well, it measures something, but it measures something slightly different than what you would get on your machine typically. Like I have a very high-speed internet connection. So like, the bottlenecks that I experience are different when I throttle versus when I don't. Because when I throttle, the network is slower. And so if we need to do things at the same time, it's easier. But when my network connection is really fast, like actually operations on the CPU can actually become, or like on-disk I/O can become blocking. Because like, maybe I'm like streaming it really fast and trying to unzip a file and write it to disk. Like the bottlenecks are just a little bit different. The other thing we'll do sometimes is like, if we do need to look at anything related to like the HTTP stack, we'll just like run a local server. So we're still, again, it's different, but gives you some information.
Some predictability,
Yeah. It's like if you're trying to like, at least then you get consistency in, to a greater degree, at least, around like what your measurements look like. Yeah. The really hard thing with network I/O is just like, it can just be all over the place. And if you're trying to measure like a 1% to 5% performance change, it's very hard to do it in the presence of making lots of network requests.
And in that context, I was surprised to learn that you're using a single-threaded Tokyo runtime. Isn't that what you're supposed to do when you want super amazing high-performance I/O in Rust? You always use multiple threads in Tokyo. Like, why did you decide against that?
Yeah, I mean, I guess like the simplest answer is just that we benchmarked it and we looked at it a lot, and then we found out that like basically we use a single Tokyo thread for I/O is sort of the way that I would put it. And we found, at least the theory, I guess, is that it reduces synchronization costs and that we don't perform like enough I/O for multiple threads to be worth it. So like we're often, what's like a lot of I/O, right? If you think about a web server that's trying to do, or something that's like super high throughput and they're trying to do like thousands of requests per second, that's like pretty different than what we're doing. Because like for us, maybe we're downloading 20 packages at the same time, right? That's 20 different requests that are happening. It's like pretty different. It's a pretty different amount of throughput. So like we found that using a single thread for I/O and then being really careful about compute work. So trying to make sure that we run compute work like off that main thread or off the main thread is also really important. So for example, like we have a solver in UV, we have to solve for dependencies, right? Like we get a big graph of the things that people depend on, and then we look at the things that those packages depend on, and we have to solve this like big constraint satisfaction problem. That solver runs on its own thread. So like we move that compute off to like a different thread. So we have to be like a little bit careful about like what we do on which thread and like how we orchestrate it. But we did like actually find in practice that it was faster to just use like the single threaded runtime. There's some nice other things to it too. Like we can use like RC instead of ARC in like some places. There's like some minor like quality of life things like that. But yeah, we just make like a lot of small network requests, and we found that like using the single threaded runtime empirically was like faster for our program. There was also a long conversation when we started UV about whether we should use async Rust at all, which is sort of another topic. Like the thinking there was like, do we actually have enough IO to demand async Rust and or some kind of multi-threaded runtime? Because like that's maybe what we would see as like the main benefit is like, okay, we get all this like thread coordination and stuff. And like I was pretty into it at the time. Like other people on the team sort of tried to talk me out of it. And we're more like, okay, why don't we just like manage our threads for doing this kind of IO? I felt like I felt like doing it with async Rust was like would be more like doing it right and maybe moving slightly more in the direction of like the arc of what the ecosystem wants. I don't actually know if that's proven to be true. Like I'm sort of like, I think we could have built UV without using async Rust and it would have been fine. Maybe I'll just put it that way. At the same time, I actually find working with async Rust to be really pleasant. And I think it's actually improved fairly dramatically even since we started the project. Like since we started the project, like the Rust team just like keeps shipping, like there's like things just keep getting like async. Now there's like async closures, async in traits didn't exist when we started the project. We had to use like the async trait macro, for example. Like there's just a lot of things in async Rust that have actually been like stabilized and improved in the last year. And I really don't find myself having to work around async or fight async, quote unquote, very much. For whatever reason. I'm not saying that it's worth it for every project, but like I actually don't think it has been a big challenge for us. I think the main challenge has been this stuff around scheduling and like trying to understand like how do we schedule really efficiently, and maybe feeling like we have slightly less control than if we were like hand rolling our own approach to threading.
I mean, in this situation, there's sort of a middle ground as well, which is instead of having a global Tokyo runtime, let's say by annotating your main function with Tokyo main, you could also use structured concurrency where the core of it is sync. And when you use a lot of I/O, when you need a lot of I/O, you can start your own little runtime, even within a function, say, or within a struct. Did you consider that approach as well?
Yeah, I think that's probably roughly what we would have done if we didn't do this. And again, I think that could have been totally fine, but this also worked. And so it's like, I don't know, it's been good. I think there are challenges with async, right? Like the things that I mentioned before are becoming less of a pain, but there's still a little bit of pain, like async closures, right? Things have to be sent in sync. It's slightly infectious, right? Whereby like if we need to call one async function from another function, suddenly like the async propagates upward. And there were some challenges like that. Like just as a random example, like our Git implementation, I originally basically vendored from Cargo, not exactly, but like I looked at Cargo's Git implementation and I was like, okay, Cargo is good at Git. How do we deal with Git? And I started with what they had, and then we changed it pretty significantly over time. But like that was an async, right? And so like, and we were like calling into it from an async, from an async runtime. That ended up actually causing like kind of a lot of problems that were like pretty annoying to debug because, for example, they need to make network requests, and it was using curl or something. And I was like, okay, but we use request. I only want to use one networking stack, so let's replace it with request. But okay, if we want to replace it with request and it's going to be sync, then we have to use request blocking. And then it was actually, for a period of time, I can't remember how we fixed this. It was actually impossible because then request blocking actually starts I believe it uses async internally. And so it was like we were starting a Tokyo runtime within a Tokyo runtime, and like that would just error, right? And so it was like we were trying to take some code that wasn't async and use it in an async context. And it was just they kind of like butt heads a little bit. So you do run into stuff like that by buying into async. But in general, I think the ergonomics of it are actually quite good. And like I don't think we pay much of a high cost for using it, and hopefully we'll get more and more out of it over time. Is a little bit of how I think about it.
Yeah, exactly. So I would assume that the majority of the problems with async Rust that you mentioned, they don't really affect you because you don't think libraries first. Your user-facing interface is the CLI. But if you were to build a library and it used Tokyo as a sort of public interface, so that it was async to begin with, then that can cause some headaches with integration.
Yes,
because
100%. Yeah, sorry. This is actually a great point. That's actually maybe the thing that's most painful about using async is like there are all these crates that we depend on that we have to depend on basically like the async versions of those crates or the async interfaces. And if I look at all those crates, they have to actually maintain like a Tokyo interface and a sync interface and maybe like an async standard interface like sometimes. And for example, like we have tar RS, okay? Really popular common crate for creating and untarring, creating tar balls and untarring them. And like we wanted like an async tar implementation. So like it turns out there's something called, I'm going to get the exact names of these things wrong because they're all so similar, but there's something called async tar, which is an async standard port of tar RS. It's meant to be they took tar RS and made it async with async standard. Well, we can't really use that because we're using Tokyo and not async standard, and we don't want to have these two huge dependencies on different async runtimes. Okay, so that it turns out that got forked to something called Tokyo tar.
Obvious.
So it went from tar RS to async tar to Tokyo tar.
Okay.
And then that crate actually got forked like 2 more times, just by different people because it wasn't really maintained. And then eventually we forked it ourselves to fix some bugs. And now we like fully maintain that. Like we just like maintain it. That's actually a public crate that we publish outside of UV, where we upstreamed or we downstreamed, I guess, a lot of things from tar RS, and we like fixed some bad bugs that users were hitting. And so the whole like the ecosystem problem, I actually have no idea how to solve that, which is like, it seems like a huge pain for crates to have to maintain all these different interfaces. And then for us, it's like we have 2 different zip crates. We use zip RS, and then we also use async zip because we have like slightly different contexts in which they run. And like that's maybe like an us problem, but like I think probably the most challenging piece is just the touch points with the rest of the ecosystem when you want to pull in async versions of things, or people have to maintain async versions of things. Like okay, we're going to maintain like this async tar crate forever because like the tar RS crate is sync. Like that's kind of a bad outcome, but I have no idea how to solve it. I don't know if that's what you're getting at. You're probably talking about it more from the library maintainer perspective of having to expose Tokyo interfaces. Like a lot of crates will have a Tokyo feature, right, that like pulls that stuff in. But yeah, it's a little painful.
I don't know what's the way out of it here, because in reality, well, the ecosystem is still evolving. Async STD is sort of dead, so that's off the table. But I do believe that there's merit in having a sync interface and then an async interface on top of that, which is a separate crate, and as the crate ecosystem allows for it. But yeah.
I actually did once, maybe just to illustrate how confusing this stuff is and how little I know about it. Like early on, I did actually pull in a crate that used async as standard, and I wasn't really thinking about it very hard. And I just saw I had like an async interface and I needed to call like .compat on like a couple things or something. And I was like, okay, cool, like this works. And then it like obviously like massively bloated our, our like dependency graph and everything. And people on my team were like, did you do this intentionally? And I was like, I don't even really know what the difference, like at that point in time, I was like, I don't really know like what the difference is between these things. They're just async, right? Blah, blah, blah. So like, it's super confusing. It is helpful that things have centralized more around Tokyo, I think, but it's a very easy like mistake to make. And it's like not all clear how these things relate to one another, honestly.
Yeah. It had a ripple effect on the ecosystem, which we still deal with today. But it's a step into the right direction that the futurist trade is now in the Rust prelude. So it feels like, as you say, things are progressing.
Right.
Now, another thing that I wanted to touch on, which also kind of is interesting because you diverge from the norm a bit, is parser generators.
Oh, yeah.
I think you decided to switch to a handwritten parser in Ruff. And I wonder, first off, what was the decision process there? And second, how do you handle the complexity that comes with it?
Yeah, great question. So like originally the parser in Ruff came from a project called Rust Python, which is, I guess in some ways like an even more ambitious project because it's a whole Python interpreter. So they're actually trying to build like in Rust, they're trying to build a whole runtime. So like as part of that though, it has to parse code. And so I took that parser and we depended on it as a library. And that parser was based on a parser generator called Lalrpop or Lalrpop. Again, I don't really know how to pronounce anything because I spend all my time just like on the internet.
Same.
But it was, it's basically like you create a Lalrpop file. It's a DSL, but it also can include like Rust code verbatim at different points. So you have something that kind of looks like the grammar. But the thing that we were finding when we started using that, the first, I guess, sign of trouble was that Rust Python didn't support several syntax features in Python, newish features, last couple of years, like match statements. Python has support for pattern matching, and that was added in 3.10, I think, and it didn't support it. And I was like, okay. And it turns out that that's because in Python 3. Oh my God, I'm going to mess this up. I think in 3.9, maybe they switched their parser. So they moved from an LR1, this is not important if you know what these things are, but they moved from an LR1 parser to a PEG parser, a PEG parser. And basically it meant that the grammar got more flexible. So they were able to have things that would be called soft keywords. So for example, match is a valid variable name. You could do match equals 1, but it's also a keyword because you can do match object, and then patterns, right? So it's both a valid variable name and a keyword. And whether it's a keyword depends on the context around it. So it depends, like the parser has to be able to support both those use cases. I'm just thinking, I think async, now I can't remember. Async might be a soft keyword as well. But largely it's for things that were added where they don't necessarily want to make changes that are backwards incompatible in the sense that like, there's a lot of existing Python code that needs to run on new versions of Python that might use match as a variable. And so that code should continue to work. So the grammar got more complicated and they added a more powerful parser to support that. Now, our parser that we were using based on Lalrpop couldn't support that. There were like ambiguities in the grammar that were very hard to represent in Lalrpop. And we had to get increasingly good at Lalrpop in order to do it. So like, in terms of like the precedence of the statements, the way that you do like basically we were just like learning this tool really deeply and having to put more and more work into actually supporting the Python grammar.
Mm-hmm.
So what it felt like at the time was there were a few properties that we wanted that we thought we could get out of a new parser. One was we thought we could make it a lot faster to start just out of the box. 2, we thought it would be much easier for us to optimize further because it's very hard to optimize like a parser generator. Like the code is generated, right, as it sounds. And so like you can't there's only so much you can do to like optimize the generated code, right? It's like kind of out of your control. And the third was error recovery. We wanted like much better control over error recovery so that, especially because we're building tooling that's designed to work in an editor. So like if you type a syntax error, like if you type def space and you're like starting to type a function, we still want to be able to parse as much of the file as we can, even though it's not syntactically valid anymore. And that's like pretty hard. Like there are probably parser generators that support that to different degrees, but like a lot of that requires fairly bespoke handling of like what happens when you hit an error and like what the different fallback cases could be. So there were things we wanted out of a parser generator, which were like performance and error recovery. And then we also found that we were spending a lot of time just trying to get the parser generator was supposed to save you time, but ultimately we were spending a lot of time trying to get it to work for the grammar in the first place. So we were like, we want to rewrite the parser. We were like pretty sure about that. And actually a contributor came to us and said that they were they wanted to write like a handwritten parser. If I recall correctly, I think it was actually for like a master's project. And they were like, would you ever like use it in Ruff if I can get it to work with the Ruff AST? Like I'm building around the Ruff AST. Sorry. They were building around the Ruff AST and they were like, if I can get it to pass the Ruff test suite, would you want to use it in Ruff? And we were like, yeah, absolutely. And we'll pay you for it. And so we,
Wow.
so we like, there was a fair amount of, this contributor like brought us this parser and there was a fair amount of kind of like last mile work of making sure that, because we're being used by all these big projects, we need to make sure shipping a parser is like a huge change. So we did end up investing a lot of time in like the final 10% of like making sure that it works in all cases and that it won't panic for people and that it will work exactly as we expect. It's the kind of thing that it's pretty easy to test at very large scale because we can compare for example, the diagnostics that we get on very large projects. There are arbitrary large projects and we can run Ruff before and after on those projects and make sure the diagnostics are completely unchanged, for example. So we did a lot of large scale testing and it was actually like an incredibly smooth release. Like I don't think we got like maybe one bug report, which is amazing. I didn't even work on this, so I can brag about it a lot, but like it's amazing that happened. And ultimately, it means we now have our own parser. It's completely handwritten, and it's been way easier for us to modify it over time because, like, it is work for sure. Like the grammar gets extended, but we have complete control over like how the parser works, and like the idea of adding new syntax to that grammar is so much less daunting than adding it to like the parser generator, it's really not meant to be a knock on the parser generator. Like I think like that's a great project. I think parser generators can definitely be great. It just depends on what you're doing. But for us, like Python, there's just a lot in the grammar. There are lots of ambiguities and it's evolving and it's something that we have to change. So we felt more comfortable doing it ourselves. And it was also like way faster. Like it sped up all of Ruff by like 20 to 40% or something.
That's pretty impressive. And it sort of paid off for you to take ownership of this entire parsing part because it's such an integral part of what you're building at Astral in general. You can probably use that for UV and for Ruff, I'm assuming. I don't know.
We don't use it in UV today. The Python parser, we don't use it in UV today, but we could. We have other parsers in UV, thankfully, like the version parser, the version specifier parser, the requirements TXT parser.
Yeah, a lot of the work that you do is parsing, right?
I guess so, yeah. I mean, often like we need to implement standards, things that have been specified in Python, but only really have Python implementations. So like versions would be a good example. Like sounds like a simple thing, like 1.0.0. Right. But like they get actually fairly complicated. And so like, it's not like that parser is incredibly complicated, but it does run, I don't know. We're probably analyzing, I have no idea what the number would be. We're probably analyzing billions and billions of versions a day, right? Think about how many times that version parser is parsing versions, right? Like, so, we think a lot about how do we make that fast and how do we make sure that it's fully standard compliant. So yeah, we do build a lot of parsers.
To me, that was probably one of the highlights of EuroRust last year, where you shared that story about version parsing. I had such a good laugh. So if someone hasn't seen it yet, we will link it in the show notes. That's
a really fun example.
Really great. Yeah, it was such a fun exercise. And I think you could make an entire course around that. But anyhow, probably a PhD, but yeah, that's another topic. Still, it's different when you build that as a fun hobby side project or when you do that as a business with multiple employees, with a larger code base, with multiple crates and so on. So I just wanted to take the opportunity to talk about day 2 with Rust as it stands today. What's the verdict?
I love it. And I think it's been such a good choice for our projects. So we can build extremely stable, extremely fast software that also has the benefit of being memory safe for like, thousands and thousands or millions, whatever, of like Python users. And the day-to-day is excellent. Like Rust, I've always thought that Rust kind of like, I don't know, it's not that much of a secret, but like the secret behind Rust is, I've always thought, is like the tooling. Like for me at least, and I've never really written any C++, and people can also just think I'm a moron, which is fine. But like whenever I look at a C++ project, it's like, it's super intimidating to figure out how do I even get this thing to build or run, or like, what am I doing? And I don't know that I ever would have become a quote unquote systems programmer through C++, or I think it would have been a lot harder for me. That's my prediction. Maybe I'm wrong. I don't know. But like Rust, it's just such a high confidence experience. It's like, you install this thing with Rust up, you run cargo build, and like that's how you build a project. Like I can clone any Rust project and like feel fairly confident that I know how to run it and how to test it and how to build it and how to understand it. And so for me, like the tooling story is excellent. I think the only things I really have complaints about, and these are just like things that people are always going to, that I'm always going to complain about no matter what, is like, obviously I'd like compile times to be faster. That would be nice. Because as you build a bigger and bigger project, it becomes more and more of an issue. And it's just like a tax on development. But, even if they were faster, I'd probably be saying the same thing and saying, I just want them to be faster. Like, that's like the main thing for me. I think one thing I'm really impressed by in Rust 2 is just the rate at which the language and the tooling keeps improving. Like every Rust release has something I want and something I've been waiting for, which is kind of crazy. Like just even looking at, and I'm not one of the, like, there are people on our team who have been doing Rust since before 1.0, right? And I've been doing Rust for a long time. And like, I started doing Rust in like 2022 is when I started writing Rust, I think.
Wow.
But yeah, I haven't been writing Rust for that long. But like now I'm like, every Rust release, like there's just so much progress, and it's like awesome to feel like you're part of this community that's like building and growing all the time. So it's both, it feels so stable and like so mature, but it's also the rate of change I think is like great, and the rate of progress and the rate at which things are being addressed. My only complaint is compile times, but I'll take what I can get, really.
Same. Let's make it faster. Definitely.
Yeah.
We need more crates in the workspaces. But when you refactor across crates, or maybe even within crates, how does it feel to you? Like, what's that experience like? Like, do you refactor with confidence? Is it something that you look forward to? Is it a joy to refactor, or is it more of a, dread?
No, I like refactoring in Rust a lot. I think like it's not like, maybe it's the nature of what we're building. Like I guess the thing that people often say about like very well typed languages or even like functional languages is like, if it compiles, it will work. I don't know if I believe that about Rust. There's still ways that your pro code can be wrong, but I do feel like I'm constantly guided by the compiler. And actually more and more, I think the way I write code is that I try and make it such that I will be guided by the compiler in the future. So like, for example, I think about this with like, okay, let's say I'm passing like a struct into a function, and like I need to do something with every field. I want to make sure that if I add a new field to that struct, I'm reminded that I need to handle that field in that function. And so the thing I will often destructure it, because that makes sure that if I add it, as opposed to referencing all the fields in line, like object.a, object.b, I will destructure it at the top of the function. It's a very small thing, but it means that the compiler will remind you that you need to look at it if you add a field. So like more and more, I find myself trying to find ways to be guided by the compiler, because it's such a powerful thing. And it just makes progress. I just think it makes like working on large complex products like so much easier.
The destructuring part I never heard in such detail, because
that's kind of a silly little thing, but you understand what I'm saying, right?
No, I totally like it. I will totally steal that idea.
Hopefully you don't have structs that are that complicated that need that much, but like, it is, I just like more and more try to think about like, how will the compiler make sure that I do this correctly in the future?
Yeah, I know about that tip in a serialization context, when, for example, you want to ensure that all the fields get serialized and deserialized properly. Then I know some people do structure that, but it never crossed my mind that you can do that in just, normal function code. You could even destructure it right there in your arguments. You don't even have to do it in the first line of the body. You can do it in the arguments because it's just a, pattern match essentially. Or like it's a destructuring pattern essentially.
Yes. Yeah.
Do you have more such tips? Like where can people learn more about idiomatic Rust and best practices? Where did you learn that?
I mean, a lot of it I learned from having great teammates, which is that's sort of a bad answer because like it just depends on your life situation. Like you don't have that much control over that. You have some control, but it is a real thing, which is I started working on Ruff on my own. And then as we grew the team, I ended up hiring, thankfully, people who knew a lot more about Rust than me. And like Mika on our team, who was like the second employee to join the company. Like he just taught me so much about Rust. And then later we hired like Andrew Gallant, Bird Sushi, who like I will often just send him random Rust questions rather than Googling them. I mean, not in a way that is exploitative of that relationship or overly burdensome on me, but he loves being kind of like the elder statesman at the company that can help people with hard Rust questions or problems. And so finding great people to learn from is maybe the slightly higher level lesson, but like I know that's not always easy. The other thing that I did is I read a lot of code. Like ChatGPT and LLMs are great, but like you should also remember that like GitHub Code Search exists and like all these amazing code bases are open source. And so, for example, something I'll often do now is like if I look at a crate and I want to use it and maybe it has great examples. Okay, great. If it doesn't have great examples and I don't feel the need I don't want to read all the documentation myself, I will actually just go into GitHub Code Search and I will just search for the struct name or the function name. And I will go find real examples in 1 second of real projects using that crate. And so like, you can just go read code, like reading code is like, all this stuff is accessible to some degree. And so that's how I've tried to pick up things and at least learn. Like I looked at Cargo a lot when we were building UV and tried to understand like, how do they do certain things? Like, I don't know how to implement Git. Like, let me go look at what Cargo does. And then let me read about their design decisions because it's all documented in their PRs and you can understand the trade-offs and you can understand like why they did things a certain way. So, you can also go hunt people down and talk to them about this stuff, but there's plenty that you can find without doing that.
Fully agree. Before there were LLMs, there was Burn Sushi, but unfortunately you hired him, so there's just one of them. But you can still read their open source code. So ripgrep, whenever someone tells me what is an idiomatic Rust crate that I should read, I always point them to ripgrep because...
Oh yeah, I looked at that a lot too. When we were figuring out how to structure our crates and how to manage workspaces and our release pipeline and all that stuff, there's just so much good code out there. And so, go read it.
Yeah, I always cry when I open the ripgrep code, out of joy, of course. I really like reading this. It's amazing. Yeah, unfortunately, we have to come to an end. But I wonder if you have any final statement to the Rust community.
Yeah, I mean, I think for me, like how do I say this correctly? Like it's kind of amazing. I think that I only started writing Rust like a few years ago, and now we've shipped. I mean, along with a great team, like we've shipped 2 of these tools that are having, I think, at least a huge impact on Python, which is like the most popular or the second most popular programming ecosystem on Earth. So if you think about it, like Rust is kind of, in a lot of ways, Rust is kind of like powering Python, at least to, if I have a say about it, at least Rust is powering Python. And so I don't know, I've always just felt, I never considered myself to be like a systems programmer, quote unquote. And most of my career, I was writing TypeScript, Python. I mean, I did some Java professionally, but like I had never, except for like a course in college, done any C. I really hadn't done any C++. And like in the span of a few years, I like learned to build this kind of software. So I don't know. I've had just like great experiences with the community and being welcomed into it and learning the language. And I think should continue to be a very important part of Rust, is like welcoming people in and helping them learn, because the impact that we can have by building this kind of stuff is just huge, even outside of Rust.
Perfect. I couldn't have said it better. Both languages are really close to my heart, and I really like to see that synergy. Charlie, your presence was much appreciated. I thank you so much for taking the time today.
Yeah, thank you so much for having me and for all the great questions. It was really fun.
Rust in Production is a podcast by Corrode. It is hosted by me, Matthias Endler, and produced by Simon Brüggen. For show notes, transcripts, and to learn more about how we can help your company make the most of Rust, visit corrode.dev. Thanks for listening to Rust in Production.